Good afternoon, everyone. This is Zhang Yan from Purple Mountain Lab. Today, I'll present our work, Topology-Adaptive LEO Satellite Network Telemetry via Graph Isomorphism and Topology Partitioning. Recent years have witnessed a resurgence of interest in satellite networking. Low Earth orbit satellite networks have many advantages: global coverage, low latency, cost efficiency, and so on. More and more applications are realized over this network, thereby result high requirements for quality of service. Network management is an efficiency means to ensure the operation and the performance. However, in the LEO satellite constellations, the high dynamic nature challenging management. For example, in the Starlink constellation, topology changes may reach 10 times per second. And the network management has been widely explored in terrestrial networks. And network-wide management requires topology-aware pipelining. For instance, INT paths need full network topology knowledge to guide monitoring paths. However, LEO satellite network changes frequently and periodically. If we directly apply a terrestrial approach, we need to calculate the paths for every change, result repeat execution and overhead. So, to achieve LEO satellite network management, we need to analyze the link characteristics and topology dynamics. LEO satellite constellations is usually local constellations. It has uniformly distributed orbits and satellite. The satellite links on or off with satellite motion. Specifically, intra-orbit SLs remain always connected, while inter-orbit SLs break or reconnected as satellite enter or exit the polar regions. This means inter-orbit SLs only existed in the non-polar regions. Meanwhile, the link switch also results in frequent and periodic topology changes. So we have a question: are there underlying patterns in the frequent topology changes? Actually, the regularity of satellite motion often results in similar graph structures among different topologies. There is an example in LEO 48 constellation, 3 topologies at different times. We can see from time A to time B, the 2 topologies have different structures, while from time B to time C, the 2 topologies have similar structures, even though the satellite IDs at corresponding positions are different. To make this into 2, let's zoom in on a part like this. Clearly, different topology snapshots may have same structure, like the topology at time B and time C. So when performing network-wide management, we only need to plan problem paths for different structure topologies, reducing the computation and overhead. Furthermore, we observe topology across the 4 petrode. In this example, this figure shows a fake link pattern of 4 different structure topology graphs appearing in a fixed order. So different structure topologies may occur in a continuous sequences, like G1, G2, G3, G4. So it's straightforward to extract them from network topology sequences. Given this, how can we use these patterns and link characteristics to measure the LEO satellite networks? Our solution has 2 main concerns. First, graph isomorphism. We find the constant in the change and configure 4 topologies using only a small set of representative topologies. We investigate this self-similarity of the dynamic topologies using graph isomorphism. Second, topology partitioning. Satellite network topology changes have regional difference. We apply a divide and conquer element method, monitoring non-polar region with anti-based path-planning and polar regions with probing flooding. And what is graph isomorphism? It's a concept when two graphs captures when two graphs are identical in structure. Intuitively, two graphs are isomorphic if one can be transformed into the other by renaming its vertices without changing the connection between them. For example, topology A and topology B are non-isomorphic, while topology A and topology C are isomorphic. And then to obtain the non-isomorphic topology graphs and quantify the benefits of probing path planning based on non-isomorphic topologies, we need to calculate the number of topology changes and the number of non-isomorphic topologies. In the interest of time, we'll skip the detailed derivation here. For the complete mathematical process, please refer to our paper. So here, we get the number of topology changes and the number of non-isomorphic topologies and the ratio of them. From this ratio, we can find the number of non-isomorphic topologies is much smaller than the number of topology changes. We can then determine the number of non-isomorphic topologies and extract them based on our equations. Next, for element with topology partitioning. Remember the LEO satellite characteristics. Satellite topology changes have regional difference, so we divide the satellite network into non-polar network and the polar network by the polar region boundary and use different monitoring methods for different regions. For non-polar region monitoring, we adopt a network-wide telemetry approach by anti-based path planning. Specifically, we first extract the corresponding non-isomorphic topologies based on our equations, and then generate monitoring paths by anti-path, then install the computed measurement plan into the data plane of LEO satellites. Finally, activate the INT logic on node satellites. Next, for the polar region monitoring, we adopt a floating-based probing approach to simplify measurement. In these regions, inter-orbit ISLs are already disconnected, so floating does not incur significant overhead. And how to deliver the telemetry data to the ground? The telemetry data connected at the INT sync nodes needs to be transmitted to the ground station. The INT sync is not the direct link satellite located above a ground station, so we adopt a relay-based data lining method. We establish a channel between the INT sync satellite and the direct link satellite, and then the telemetry data are sent to the direct link satellite and then delivered to the ground station. We conduct experiments to validate our derivation of change nature and evaluate the proposed measurement approach. This table shows satellite constellations of different seeds and types. From this table, we can see the number of non-isomorphic topologies, that is NOI, is much smaller than the number of topology changes, that is NCHG, which verifies our proposed equations. And next, for path planning execution time, it refers to the time required to generate monitoring paths for all network topologies. And our solution significantly reduces this time compared to directly using anti-paths. Time for one round of telemetry. It refers to the time required to complete one round of network-wide telemetry. And the telemetry time of our solution is lower than that of anti-paths. For example, in the constellation with 100 satellites, our solution reduces the telemetry time by 25%, compared to antipaths. In summary, we present a topology-adaptive telemetry approach for LEO satellite networks, reducing monitoring overhead while ensuring fine-grained network visibility. We observe self-similarity in topology changes based on graph isomorphism, which allowed us to represent the 4 topology sequences using a small set of distinct topologies. We apply a divide and conquer strategy monitoring in both polar and non-polar regions by topology partitioning, enhancing scalability and efficiency. And in the future, we plan to explore from the following directions. First, we plan to place the INT source and sink directly on ground station to achieve end-to-end management. Second, we plan to explore management approaches for virtual satellite networks. Third, we also intend to explore topology-agnostic management, reducing topology dependency. That's all. Thank you. Any questions?
Okay, thank you. Any question?
Hello, thank you for your presentation. It's an excellent work, but I still have some questions. That nowadays the LEO mega constellations, they sometimes is kind of mixture like a Starlink. They have version 1, version 2. They may own different layers. Whether this kind of approach can still apply to this scenario, is still the topology partitioning is still work? Because sometimes the phased radar, they can move and the layer can be different. So that's my question.
You mean the constellation may have different layers?
Yes, yes.
Actually, when we just analyze this the topologies in the same layer.
Yes. So is the topology partitioning, this kind of method can be applied to different layers, is my guess.
Actually, for most constellations, the satellite is in the same height, but as for some constellations like Starlink may have different layers. But the different layers, actually, it can be it's like a site of constellation. So when we performing pipeline or other, we just considering the one constellation in this set of constellation.
Okay, thank you.
Any other questions?
Thanks for the talk. So I'm Shuai Hu from Huawei. So I'm just wondering, have you calculated the bandwidth overhead for doing your probing, over the whole satellite network? I mean, bandwidth needed for your probing.
Floating. Floating.
Probing. I mean sending packets around different nodes in your satellite network. The traffic. The traffic.
You mean the probing overhead?
Yeah.
The overhead. Our experiment is indeed a bit simple. We also have considered the experimental setting like the overhead, but this and I will enrich this part in the future work.
Okay. Yeah, we can discuss more offline. Thank you.
Okay. Let's thank our speaker again.